Okay. All right, we are going to go ahead and get started. So, this first part, hey, if you don't know me, I'm Miss Cyrus, and I run my class. I run a tight ship. And the reason why my kids are so successful is because when I'm teaching, you're not talking, okay? If you want to talk, raise your hand. We also have fun, and we can have fun, because solubility is actually really cool, and it is literally in your day-to-day life. Like your Starbucks drink has to do with solubility. Did you know that?
No, I did not.
Well, now you do, right?
Yeah.
So, all I'm saying is you have a quiz on Friday over some of the stuff that I'm teaching you today, the stuff you're learning next class, and the stuff Miss Tillman taught you day one. So it is very important that you pay attention. This first part on this page, it's just a review. So it's what you learned last class. So A and B, I'm going to give you about a minute and a half, and I want you to talk to your table. Okay? If you don't want to talk to your table, then you can talk to yourself. I want you to talk about what you learned from day one, fill this box in, and then what factors affect the reaction rate and solubility of solids in water. I want you to just do A and B with your table. Okay? Ready, set, go. That would mean that polar dissolves polar, right? And nonpolar, I'm going to abbreviate that to NP, dissolves nonpolar. This saying like dissolves like is the exact reason why oil and water do not mix. Because water is polar and oil is nonpolar. It doesn't matter how much oil or how much water you have, they're never going to mix, right? They're never going to. That's what this saying is basically hinting at. All right, the next part. What factors affect the reaction rate and solubility of solids in water? Who can tell me one factor? Let me say it a different way. What is going to allow me to make sweet tea in the most effective way? Temperature, so heating it up. What else? Stirring it. So heat it, stir it, and what else? Crush it. So if you remember, heat it, stir it, crush it, you're good. Those are your factors. So it's better if I use granulated sugar than sugar cubes. It's better if I am stirring my sugar in my tea rather than just adding my sugar and letting it sit there. And then it's even more effective if I heat it up. I mean, raise your hand if you've ever ordered sweet tea and they give you iced cold tea and sugar. Does it work? No, you're sitting there, you're going to get arthritis from having to stir for like 30 minutes. It's not the same. Okay? All right, this last part of this review says determine which of the following graphs depicts the relationship between a solid and a gas. So we talked about, well, not we, but Ms. Tillman and y'all talked about the relationship between temperature and solubility when it comes to a gas and a solid. So for a gas, if I increase the temperature, let's say in my Dr. Pepper. If I have a Dr. Pepper and I increase the temperature of it, what's my Dr. Pepper going to taste like? Flat, right? Because what's going to happen to the pressure? Or not the pressure, the solubility. It's going to decrease. When we say that my gas in my Dr. Pepper is going to decrease, we're saying the carbonation. Carbonation's a gas. So our graph looks like this. As I increase my temperature, my solubility is decreasing. Does everybody see that? If you need to think of soda as a way to remember that, do it. That's a good way to remember. All right, so temperature and solubility for a solid. What do we think our graph's going to look like when we increase our temperature? What's going to happen to my solubility? Increase. Just like I was saying for making sweet tea, when I increase my temperature of my tea, am I able to dissolve more sugar? Yes, that's the whole reason why Chick-fil-A has the best sweet tea. Or chickeny, whatever you want to say. But if you say McDonald's, that's false. told you I don't lie. I did. All right, pressure. What happens with pressure and solubility for a gas? Let's go back to our Dr. Pepper. If I had a Dr. Pepper and I haven't opened it yet, can you squeeze your can? No, right? It's very pressurized. So the moment that you open your can, everybody make the noise that happens whenever you open your can. Or open your bottle. What sound makes? Right? Pressure is being released, gas is being released. Okay? But the moment we have that high pressure, what is at the peak of our solubility? Is it at the peak or is it at the pit? When our pressure is really increased in a gas. Peak, right? That's what our graph looks like. And then what about pressure for a solid? What did Ms. Tillman say in regards to pressure for a solid? If I increase the pressure of my sugar cube, is anything going to happen to the solubility of it? No. So it's going to have no effect. So that's why my graph looks like this. Do we have any questions on this first page? All right. Next page. This is known as a solubility curve. So a solubility curve is showing the relationship between solubility, and that's going to be in grams, and temperature. Okay? Solubility and temperature. It's important to note that this is saying grams of solute per 100 grams of water. That's super important to recognize, because I could ask you a question about something for 200 grams, and then you would have to set up a proportion. So always make sure that you look at your X and Y axis. Okay, before we start answering these questions, one thing that I want you to write down is the term saturation. And I want you to talk to your table for about 30 seconds on what you think the word saturation means. Talk with your table on what you think the word saturation means. Ready, set, go. Ten more seconds. All right, somebody raise your hand and tell me what you think the word saturation means. What do you think the word saturation means? Drenched. Okay. So that is another term of it. Yeah, 100%. Like when you're editing a photo, one of the words is saturation. Yeah. Yes, for sure. That's really good. Somebody else. Saturation. I want you to try to think of it in the terms that we've been talking about, like with solubility and all of that. Okay, somebody tell me what you think it means if I had a sponge. What would a sponge that's very saturated look like to you? Big? Okay, so that would mean that SpongeBob was full of what? Water or some sort of solution, right? When something is saturated on a solubility curve, it's going to be on your line. That's important to recognize. Okay, what about if SpongeBob was looking a little dry? Unsaturated. If it's unsaturated, that means that SpongeBob still has the ability to absorb or dissolve more of something, right? That would be below your line on your solubility curve. And then the last term is if SpongeBob has so much liquid that some of the liquid's coming out, that would be supersaturated, okay? That means that you have reached your peak, okay? In order to have something that's supersaturated, sweet tea is an example of a supersaturated solution. You have to heat it up, because when you heat things up, you're able to dissolve more. So this is your definition for saturation. It's the state or process that occurs when no more of something can be absorbed, combined with, or dissolved. Okay, so for the next 9 questions, we are going to be referencing our solubility curve. So this first question says, what type of solution is represented by 50 grams of KCl and 100 grams of water at 75 degrees Celsius? How can you tell? So question 1, 2, and 3 are just asking if our solution is saturated, unsaturated, or supersaturated. So I'm going to go to 50 grams, and then I'm going to go to 75 degrees Celsius. And I'm just going to go until I meet, and I'm on the line. But before you write saturated, you have to make sure that it's KCl, because that's what this question's talking about. Like, if this question was referring to NaCl, what would that solution be? Right now, what type of solution is this for KCl? Is it saturated, unsaturated, or supersaturated? Saturated. Remember I said, if it's, let's go back, let's look. If it's on the line, that's saturated. If it is above your line that it's talking about, that's supersaturated. And if you need to write this down, I would. And if it's below the line that you're referring to, that's unsaturated. So for KCl, if it's on the line, what type of solution is this? Saturated. And we can tell because it is on the line. All right, number 2 says, what type of solution is represented by 65 grams of KCl and 100 grams of water at 60 degrees Celsius? So I have 60 degrees Celsius, and I have 65 grams. So I'm going to go up till we meet right here. What type of solution is that? Supersaturated. And we know that because it is above the line. All right, what type of solution is represented by 40 grams of KCl and 100 grams of water at 80 degrees Celsius? So 80 degrees, 40. Jordan, what type of solution is this? Good. Does anybody have any questions on 1, 2, or 3? I'm just going to be completely transparent with you. Those are the easiest questions we will ever ask you in regards to solubility curves. All I'm having you do is just read a graph. Some of it is. Some of it's not. All right, number 4. How many grams are needed to create a saturated solution of KClO3 at 50 degrees Celsius? So if this question's asking for us to create a saturated solution, what is it saying that it wants me to look like on the curve? Does it want it to be above, below, or on the line? On the line. So that's what we're looking for. Can you grab that? Thank you. So I'm going to go to 50 degrees Celsius. and I have to find KClO3. So I'm going to take my line all the way up to right here because I want it to be saturated. So I'm on my line of KClO3. I then have to just work my way over to see how many grams that is. So how many grams do you think this would be? Because it's not directly in the middle. It's not... What do you guys think? 16? Bless you. Anybody say anything else? If you thought anything differently, I want you to say it. Just because there is a range of answers we would take. So I want to make sure, like, if you thought something other than 16, so I can let you know if you would accept it or not. 18's too high.
17.
We would accept 16 or 17. Anything other than 16 or 17 wouldn't be accepted. Because 15, like I said, it's not right in the middle. 18 is a little too high, so 16 or 17. All right, number 5. At what temperature would 10 grams of KClO3 create a saturated solution? So this is the same type of problem. It's just flipped. We're still using the same compound, but now we're looking at 10 grams, and I'm going across. Boom. Right whenever my line hits, I just look down, and what's that temperature? 30. Now there's no range for this one because that's right on 30. And you need to make sure, obviously for number 4, you put a G for grams. And then at what temperature? If you just put 30, you will lose points because are you talking about Fahrenheit, Kelvin? No, we're talking about Celsius. Bless you. Oh my God, everybody's sneezing. If y'all get me sick, I'm gonna be pissed. Okay. Did you take your allergy medicine this morning? Must be the pollen, you know. All right. Number 6. A saturated solution of KCl was cooled from 70 degrees to 30 degrees Celsius. How much solute will drop out? Does anybody know what that means? How much solute will drop out? Anybody want to take a guess at what you think that means? Solute? Well, what is this? What is solute? What is solute? What's solvent? Is the solute what's doing the dissolving or what's being dissolved? What's being dissolved, right? The solvent is what is doing the dissolving. Remember, your universal solvent is water. Okay? So again, I'm going to go back to sweet tea because it's just an easy example. What is my solvent in sweet tea? My solvent. The tea, because that's what's doing the dissolving, right? My solute would be the sugar. So if I have my tea and I heat it up to 70 degrees Celsius and then I cool it down to 30, the solute that would drop out would be what? Sugar, right? That's what would be at the bottom. That's what this question's saying. So what I'm going to do is I'm going to find KCl, and I'm going to go to 70 degrees, right up here. How much do you think, gram-wise, that is at 70 degrees? Not 50. It's not directly on the line. I would say 49. Okay? And then we're going to go to 30. How much do we think that is? Not 33. Look right here. I would say it's not directly in the middle. So I would say 36 or 37. I'm going to say 37. So if I need to figure out how much solute would drop out, am I going to add or subtract these? Subtract. Oh. 49 minus 37. What do we get? What is 49 minus 37? 12 grams. right, number 7. Number 7 has 3 parts. It says, which substance is a gas? Which substances are solids? How do you know? So we could go back to our front page, okay, and look at these 2 graphs, because these 2 graphs are showing solubility of temperature in regards to a gas and a solid. So the first part says, which substance is a gas? So out of all of these substances, which one's a gas? Which one is showing a decrease in solubility as we increase temperature? What? You said what? KCl is going up. So so it's cesium sulfate. Does everybody see that? If I need to go back over it again, let me know. I promise a question like this will be asked on your quiz and test. And I know that because I made your quiz and your test. Yes. Sure. So, if we go back here, when we were talking about a gas, right, it said as we increase the temperature, our solubility decrease, so it's going this way, okay? So if we look, is CaCl2 going this way or this way? So it's increasing in solubility as we increase temp. Same with KCl, it's going up. NaCl is staying stagnant, but it's going up. KClO3 is also going up, right? But if you look here, cesium sulfate's going down, which is showing that it's a gas. Okay, so as our temperature is increasing this way, see we're getting hotter? What's happening to our solubility? It's going down. Okay? So then which substances are solid? What would you say? Everything else. And then how do you know? When we increase the temperature, we increase the solubility for solids. When we increase the temperature, we decrease the solubility for gases. All right, number 8. If 10 grams of KClO3 are present at 90 degrees Celsius, how much more should be added to make it saturated? So if we want it to be saturated, that means we want it on the line. So I'm going to go to 90 degrees, and I'm going to go all the way up until I'm on the line of KClO3. And if I go over, that's 40 grams, right? 40 grams is on the line. Well, if it says that 10 grams were already present, 40 minus 10 equals 30 grams that need to be added. Does everybody see how I did that? Does anybody need me to go back over it? Speak now or forever be confused. Okay, last one. Which solute is the least soluble at 0 degrees Celsius? So it wants to figure out at 0 degrees Celsius, right here, when I go up, what is the first compound that I hit? KClO3. That's saying that at 0 degrees Celsius, KClO3 only has a solubility of maybe like 4 grams. That's really low. The next part of the question says, which is the most soluble? So for most soluble, I'm just going to go all the way up until my last compound, which is what? Perfect. Does anybody have any questions on 1 through 9? Yeah. When she gets back. Mhm. So on number 8, it says, if 10 grams of KClO3 are present at 90 degrees Celsius, how much more should be added to make it saturated? So I'm going to go to 90 degrees Celsius, and I'm going to go all the way up until I reach my line, because that's saturated, right, of KClO3. When I go over, I'm at 40 grams. So if I have 40 grams, and I already had 10 when I started, 40 minus 10 gives me 30 that I need to be added. Does that help? Hello? Okay, for the remainder of class, I'm going to pass out to you this worksheet. It's front and back. That's what you're working on for the remainder of class. No, it is not optional.